All right, so I think that I got cut off on the last problem, and I just wanted to kind of go back over and make sure that we're kind of understanding that. We were looking at the tensional force in the x direction from our rope was what we're saying is going to be equal to our net force, okay? Our net force being our centripetal force. So now we set it up so that our tensional force is equal to our centripetal force, and we got a centripetal or a tension force in the x direction equal to 1.125 newtons. And I think that's about where I got kind of clear. And then all of a sudden I had a little technical difficulties, and I wanted to make sure that we can then equate from that tensional force in the x direction back into what was the original tensional force, because that's what they're looking for here. So I'm using the trig function again, okay? I'm just setting it up where I've got my triangle, and I said that's 70 degrees, and this is my f of t x, and this is my f of t. So in other words, hypotenuse, side adjacent, cosine. Cosine is the adjacent over the hypotenuse, and then that gave me an answer of 3.29 newtons. Okay, so that's how we kind of go about doing that. All right, so hopefully that kind of clears that one up. I'm going to go on to a new example now, and so this is going to be our Ferris wheel example. So now we're looking at our Ferris wheel. It has a radius of 14 meters, and it's now going to be rotating. We have a person that's going to be sitting on the seat down here, and we want to find out what is the magnitude of the normal force, okay? Because remember, a normal force is just a force that's in contact between two surfaces, and it always acts perpendicular to those two surfaces. So in other words, I'm going to use a point. Again, draw a free body diagram. So here's a point that represents the mass of my person. My person has a weight that acts down, and they have a normal force that acts up, okay? Now, I drew my picture because my normal force has to be bigger than my weight at the bottom, because again, we're rotating, which means that we have an acceleration, and anytime we're rotating and have an acceleration, we have a net force. So my net force is actually bigger in the force normal than it is in the weight going down, okay, because I have to have a net force acting up, okay? So in other words, I'm going to say that my net force, okay, and net force in this sense is my centripetal force, is going to be equal to my force normal minus my force of weight, okay? Again, I'm relating it back to the fact that I've got a bigger force here. My net force is equal to that. Now, again, net force in this sense is centripetal, so I can replace Fc with my m, and I'm going to use r omega squared because I have a radians per second. I know the speed in radians per second, so I want to use an angular velocity. My force normal is what I'm looking for, and my weight of my person now just is going to be the mass of my person times gravity, okay? So now I'm going to solve for my Fn. Fn now just equals my m r omega squared plus my mg, okay? So now I just have to plug some values in. So 75 is the mass of my person. The radius was 14 meters. The omega was 5 radians per second, okay? And I have to square that, plus, again, 75 kilograms times 9.8 meters per second squared, okay? So I'm just going to go through and solve by parts. So again, I'm going to take my 75 times 14 times 5 squared, and I get 26250 newtons plus 75 times 9.8, 735 newtons, for a grand total of 2 26985 newtons. Now, the second part of this question was, what is it at the top? So how does this change if this represents the bottom when we get to the top? Okay. Now, again, at the top, we're going to draw a new free body diagram because now we're up here at the top. We have our weight, which is still acting down, so F of G still acts down. And that arrow is going to be the same size as what I had from before. My force normal now has to be considerably smaller. Okay, and it has to be smaller because I have to have a net force acting towards the center. So my net force acting towards the center, okay, is going to be the F of G minus the F of N. Okay, so I'm going to do basically the same exact thing that I did in the problem before, except now my centripetal force is equal to my force of gravity minus my force normal. Now, if I want to get my force normal, I rearrange my equation so that force normal is now equal to Fg minus Fc. Okay, so I'm going to set that all up again and just do another problem just like what I did here. Okay, except now I'm subtracting my centripetal from my Fg. Okay, so again, my force normal is going to be my mg minus my mr omega squared. And I'm going to then get my 735 newtons minus my 2,6250 newtons. And I think I'm writing on myself here. And then try this. 735 minus 2,6250, and I get a negative 25515. So really, my force normal is actually acting down because of the negative value, but it's a smaller force normal as well. Okay, so again, I'm looking at this in terms of how the two forces interact and which direction are they going to go. Okay, remember that my net force, because of the rotation, is always acting towards the center. Okay, here's my fourth example. Okay, I've got a piece of candy that I'm going to have on a turntable. Okay, so here we go. Piece of candy sitting on a turntable. Definitely not a Skittle. Must be a black jelly bean. So I've got my piece of candy. It's on the turntable, and the turntable is spinning around. Okay, so in other words, I want to know what's the coefficient of friction that actually keeps the thing from sliding off. Okay, because we've experienced this, and you maybe even did this when you were playing with the ladybug rotation simulator, that you could get the ladybug to make noise. Okay, when you spun the turntable too fast, the ladybug flew off. There was no force holding the ladybug on there. Okay, so you exceeded any possible force of friction that the ladybug could have had, and so the same thing's going to be true here. So I'm going to start by looking at the free body diagram of my piece of candy. My piece of candy has a weight. Okay, there's contact between those two surfaces, so it's going to have a force normal. Okay, and then I'm going to say that it's going to spin around, and so this is going to be my force of friction towards the center. Okay, this is the center direction. Now, again, the general motion is that we don't want the candy to fly off this way. We want the candy to stay put. So we have to know that there's going to be a force of friction that's going to act that direction. Now, the candy isn't going to jump up or down off of this. So in other words, the force normal and the force of gravity are going to be equal to each other. Very much what we did in previous problems in this class. So we have our force normal, we have our weight. They're going to balance each other out. So the size of those arrows are going to be the same. That means that the only net force that we have acting on us is the force of friction. So in other words, my net force is equal to my force of friction. Okay, centripetal force will be equal to my force of friction. So my centripetal force is going to be my mass times, and now I'm going to look here, I've got RPMs. Okay, I think I'm going to do this with an R omega squared. Okay, because I can convert 33 RPMs into radians per second. Okay, and that'll be one of my tests that I'll have to do. My force of friction is going to be my coefficient of friction times a force normal. Okay, but remember, in this case, force normal equals force of weight. Okay, so I'll just make this mg. Okay, now what am I looking for? I'm looking for the coefficient of friction that keeps everything in place. Okay, so in other words, it's the minimal amount of coefficient of friction that could make them stay put. The other option would be and this might be a different problem, a different problem could ask, okay, given a coefficient of friction, how fast would the turntable have to spin in order for you to exceed that? Okay, so in other words, we could look at it in a rotational standpoint. All right, so continuing on with this, I know the mass of the piece of candy. Okay, the mass of the piece of candy is 0.015 kilograms. I know the radius, which is 0.1 meters. Okay, and now I'm looking for my omega, and I need to do a conversion. So I'm going to go 33 revolutions per minute. And I'm going to change from revs to radians. 1 rev is 2 pi radians. And I'm going to change from minutes to seconds. And in 1 minute, it's 60 seconds. Okay, so I'm going to do that math quick. 33 times 2 times pi divided by 60. That gives me 3.454 radians per second. Okay, and I'm going to use that up here in my omega. So it's 3.454 radians per second quantity squared. That's going to be equal to my coefficient of friction times my mass, 0.015 kilograms times 9.8 meters per second squared. Okay, so again, I'm just going to go through and solve now for my coefficient of friction. So 0.015 times 0.1 times 3.454 squared gives me this value, 0.0179. Okay, equals my coefficient of friction times, and I'll figure that out, that's 0.015 times 9.8, 0.147, divide by my 0.147, coefficient of friction then equals 0.122. Okay, so again, that's kind of how we can go through and work on these problems. We want to make sure that we're kind of understanding that the centripetal force is nothing more than a net force, and it's not part of our free body diagram. So we always have to then look and say, well, what is the force that's in the free body diagram that's causing the rotation to stay put where it's at? Okay. So hopefully that worked well, and I'll see you in the next video, or I'll see you in class actually.